So in a previous video, we saw how quantum mechanics led to a description of the hydrogen atom as having particular quantum numbers that were used to describe the radial and angular components for the wave functions. This is the treatment coming from the My Honors General Chemistry textbook, Atkins. We're now going to continue on and learn more about the particular atomic orbitals, in particular their shapes and this idea of the radial probability function. So we are going to begin by looking at s orbitals. We've seen that based on their L value, we would describe orbitals as being s, p, d, or f. We already have this idea that if you take a wave function and square it, we get what's called the probability density. We're going to see within this discussion of the probability density is that if we also account for the area that's present, we get a new idea which is called the radial probability distribution function. So here we have the radial wave functions for the s orbitals for hydrogen. So each of these would be starting at the nucleus, and we're looking radially from the nucleus as we go from the center outward. Now, this isn't static. This would be going up and down, up and down. It's a wave after all. And the radial wave function can have positive or negative regions. Within our 2s, you notice one region here is positive, while the other region is negative, and those would be flip-flopping it so it goes back and forth, back and forth. When we square the wave function to get the probability density, we no longer have the negative regions there. Instead, we find that it's going to lead to the presence of nodes. So the spot where it crosses 0 in the wave function itself leads to a node. It's squared, so it's all positive values. Go ahead and square the 3s. You'd see the same thing. A node here, a node here. Before you'd done that, the 3s would have different signs like positive, negative, and positive for the phase. The description of the wave function at the bottom here, it's showing in both directions. So if this was the nucleus, you could go out in one direction or out in the opposite. We usually show the wave function as it's depicted there at the top, just starting with the nucleus and going from the center outward. But this would be recognizing that it has both a left and a right component, and these would be in turn going up and down, up and down. This fits our description for what a wave function should be. It needs to be continuous. I don't see any discontinuities there. Single valued, so for a given distance, I only have one value for the wave function. Notice that we have radial nodes beginning not for the 1s, but for the 2s and 3s. Those would be the instances in which it crosses the 0 value. And then also the boundary condition here is that if you move out far enough, you're going to have 0 probability of finding the electron. So that's why we see all of them converge as the distance gets larger and larger away from the nucleus. So these would be then the different probability density functions. We've taken the wave function and squared it for the 1s, the 2s, and the 3s. The next idea is the radial probability distribution function. This will be taking the probability density and then accounting for the area. If it's a sphere like a 1s orbital, we would have a description for the volume of the sphere. Notice how this has changed each one. So in terms of the probability density, having squared the wave function, notice the value is right at the nucleus. It's a very high value. Once we account for the volume that's present, it becomes a very small value. It's not 0, but it's a smaller value. So notice how the shapes here have shifted. What's going on within this one? I find this one as a classroom demonstration I do is helpful. So in my picture here, this is a top view. That's me in the center of the class, and I have the different students in desks around me. I point out that, let's say, my most immediate neighbors, I have 4 different students around me. I could have a very high proportion of those students, let's say, be where the electron is found. It could be 75%, but I only have 4 students right around me, so that would be only a total of 3 options where the electron could be found. If I move further out, I could have a smaller percentage. Now it's only 6 out of 12, but 6 is larger than 3 because I just have a lot more options where it could potentially be found. So this is the idea that the right near the nucleus, there might be a very high probability, but there's not very much volume right near the nucleus. If you account for the volume that's there, that's what leads to this particular shifting. That's what leads to the radial probability distribution function. It's accounting for the amount of volume that's present in a given region. So if we look at these depictions then, 1s, 2s, 3s, are these showing radial wave functions, the probability density, or the radial probability density? I think those are all descriptions for the radial wave function. Good takeaway within that is if we look at the 1s, notice how it goes to a very large value closer to the nucleus. Notice for the 2s and the 3s, we have values that are 0, or excuse me, are negative. So we definitely have not done anything as far as squaring it or accounting then for the volume. Here's different descriptions for the hydrogen atom in a 1s orbital. So at the top here, this would be then the wave function. We mentioned before how there's both a radial and an angular component. So this would be that particular description. A radial distribution plot, looking at the probability distribution and then the resulting atomic orbital. I'm using each of these. I'm grabbing them from the site my colleague Dr. Spinney has put together. So for each of the atomic orbitals, you can click on it and see the description. So again, this would be the wave function that includes both a radial and an angular component. This would be after accounting for the volume, the radial probability distribution function. This atomic orbital then is being described by saying, well, where does the electron? At a given instant, it could be here, 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 here. Overall, the atomic orbital, when we see the sphere, it's usually describing a particular probability, like 90% of the dots would be found within a particular volume. This is a great website for exploring any of the orbitals. 2s, notice we have a different wave function. We have a node present. Within this one, he's trying to demonstrate how there's 2 different phases that were there. This is after having squared it. Before squaring it, we'd have both a positive and a negative region. After having squared it, it all becomes positive. If we want to retain the phase information, we see we would have 2 different parts. And that's what's being shown within here. 2 different regions that have different phase in the wave function itself. Sometimes it's helpful to slice it in half to be able to see those different parts. Great website for playing with. Different things that we can seek to illustrate. So this is for a 1s. I find within this one, as I've gone to a 3s, the idea that we have radial nodes present. And what that I also really like the description here as far as dots to show the probability distribution. This was when we were looking at both a left and a right for an s orbital. This is the typical radial wave function for a 2p, meaning that it's only showing from the center out in one direction. If we were to look at it both in terms of having a left and a right, this is what it would look like. You notice it has different phases. So this would be oscillating up and down, up and down. If one's positive, the other one's negative. We also see that for a p orbital, we now have an angular node. Because it's a p orbital, it's crossing our axes right here at 0. So we have 2 different regions within that. That wasn't found for our s orbital. This would be then a 2p. We just mentioned that it's going to have 2 different phases. That's why it's being shown here with two different colors. Three different orientations, px, py, and pz. We move to a d orbital. I find the contour plot for this one interesting. In my first semester, we generally want to be aware and be able to sketch these particular d orbitals. In the second semester, we do more putting the labels on them. There's two angular nodes found when we get to a d orbital, so you can slice it two different ways. Here would be a 4D. So the first time we have a d orbital, there is no radial node. Second time we have a d orbital, meaning we go from a 3D to a 4D, we now have a radial node, and we have a feature inside of the outer feature. For the f orbitals, don't do much with those, so this is really just showing what those look like. You notice that when we've been looking at our radial and angular wave functions, we've needed three quantum numbers to describe that, n, l, and m sub l. Schrodinger's theory didn't account for spin. That's our last one. That's something that arises with another experiment. So the spin of a particle, this is Atkins' description, is its intrinsic angular momentum. It's a fixed characteristic, just like an electron has a particular charge. Electron has a particular spin to it. At its core, it's purely a quantum mechanical phenomena. So a lot of the analogies that one uses as far as like a spinning top, really not appropriate. Or we might say it's an analogy, but it's a potentially misleading one. One of the implications for spin, however, involves the Pauli exclusion principle. Because they have half integral spins like spin plus 1/2, spin minus 1/2, that has implications as far as if they can be found in the same region of space, which is really what the Pauli exclusion principle is all about. Within this video, as we've looked at different orbitals, we've definitely spent time with the s orbital and the p orbital. And we've looked at different ways of trying to express them, describe them in terms of a wave function, probability density, or this radial probability distribution. I think that these are important descriptions for different reasons. For the wave function, recall, is the one that has phase information. I need that idea when I come to molecular orbital theory because the phase is going to be relevant when I'm taking atomic orbitals and making molecular orbitals. For the probability density, one thing that illustrates is that an electron in an s orbital has a non-zero probability of being found at the nucleus. Electrons, when they're s orbitals, they can be found at the nucleus. The p orbital has an angular node there, it cannot. The radial probability distribution, in many ways, I find this the best description for where the electron may be found, because it's taking the probability density and it's also accounting for the amount of volume that's in a given region of space. So when I'm moving forward and I'm trying to now see where the electron is found, for example, if I'm thinking of a topic like one electron shielding another one, I find the best way to think about that is in terms of the radial probability distribution function.